Hello, I'm Russell Lai. Today I'm going to talk about threshold password hardened encryption services. This is a joint work with Julian Brost, Christoph Egger, Fritz Schmidt, Dominik Schroeder, and Markus Zoppelt. Let me first recall the setting of password authentication that we take part in every day. In this scenario, we have a client and a server. First, the client sends his username and password to the server. The server, who holds a database in which he stores a sorted hash, and perhaps some encrypted data under the username. After receiving the username and the password from the client, the server checks if the hash value of the salt and the password and the given password equals to the sorted hash stored in the database. If so, then he decrypts the encrypted data from the database and returns the plaintext value to the client. There are some issues of this basic password authentication mechanism, however. First, the hash table is subject to offline guessing attacks, and also the server knows the decryption key anyways, so an insider attacker can easily learn all the sensitive data of the clients. Password hardened encryption, or PHE, was introduced to resolve exactly those two issues. In this setting, we have a new party called the rate limiter. In PHE, the interface for the client is exactly the same as in password authentication. Namely, the client first sends his username and password, and given that the password is correct, he should receive a decrypted message afterwards. However, the mechanism for checking whether the password is correct is replaced by a PHE decryption mechanism. In more detail, the server inputs his secret key and a database, which now stores under each username a salt and a ciphertext, and the rate limiter inputs a rate limiter key RK. To check whether the password is correct and then decrypt the ciphertext, the server first sends the salt to the rate limiter. The two parties then jointly compute a decryption protocol, after which the server should learn the message, given that the password is correct. The rate limiter should learn nothing other than the salt and perhaps also whether the password is correct, but nothing else. A PHE scheme should be secure unless both the server and the rate limiter are corrupt. There are two distinctive features of PHE, the first one being per client rate limiting. Let's consider a corrupt server who wants to learn the password and hence the secret data of the client. Note that an offline dictionary attack is no longer possible, as the ciphertext must be decrypted with the help of the rate limiter. Therefore, to decrypt or to learn the secret client data, the corrupt server must communicate with the rate limiter and engage in the decryption protocol several times. However, after seeing the same salt several times, the rate limiter could refuse to answer any further decryption request for this salt and hence for this client, and therefore preventing online dictionary attack. The second feature is key rotation. Here we imagine that one of the two parties is compromised, namely that his secret key is learned by some other third party. In this case, the rate limiter and the server can engage in the rotation protocol, which refreshes their secret keys to SK prime and RK prime respectively. Moreover, the server gets an update token tau, which can then be used to locally update each ciphertext to a new ciphertext which is compatible with the new secret keys. Note that the server only needs to communicate with the rate limiter once to rotate their secret keys, and afterwards the server can update each ciphertext locally, regardless of how many ciphertexts there are in the database. There is, however, a huge problem of PHE, that is, it has a single point of failure. Here imagine that the rate limiter goes rogue and simply refuses to answer any decryption request. So in this case, the client simply loses his data and the server loses money and maybe reputation. So this is clearly very bad for both the client and the server. A natural solution to this problem is to introduce more rate limiters in the hope that even if some of them are corrupt, the whole system remains secure. To make the notion more realistic and more interesting, we assume that the rate limiters do not communicate with each other, but rather they only communicate with the server. The syntax of this new notion, which we call threshold PHE or TPHE, is as you would expect. As before, the interface for the client remains the same, and the decryption protocol between the server and the rate limiter is replaced by a multi-party protocol between the server and several rate limiters. As the name TM threshold PHE implies, we want a TPHE scheme to be secure unless both the server and more than T of the M rate limiters are corrupt. A related notion that is worth mentioning is that of password protected secret sharing, or PPSS. PPSS has a similar basic functionality, Namely, it allows to share a message with respect to a password into m shares, share 1 up to share m. Then, given more than t of the shares and also the password, one can recover the message, just like in PHE or TPHE. However, the two distinctive features of PHE and TPHE are missing, namely it does not support per client rate limiting and it does not support Key.Rotation. At this point you may wonder, isn't going from PHE to TPHE trivial? For example, a naive idea of building a TPHE scheme is to secret share the message and then PHE encrypt each secret share. However, as we can see in this proof, this idea doesn't work. I will show you an attack. So first the attacker corrupts the server and rate limiter 0, which he is allowed to. Then he instructs these two parties to run the decryption protocol so as to learn share 0. Now he uncorrupts rate limiter 0 and then repeats the same process with rate limiter 1 and also rate limiter 2. This allows the attacker to learn share 1 and share 2, and note that at each point only the server and one of the 3 rate limiters are corrupt. By learning all 3 shares, the attacker can recover the message. Another naive idea is to emulate the rate limiter using a general-purpose secure multi-party computation (MPC). However, general-purpose MPC is computationally expensive and also highly interactive. Therefore, it is not an option for practical systems. Another aspect that makes constructing TPHE non-trivial is that assuming each rate limiter learns whether the password is correct after the decryption protocol, then we can conclude that 2-round TPHE decryption cannot exist. To see this, let's say a 2-round TPHE decryption protocol indeed exists. Then we show how an attacker can learn whether the password is correct by just corrupting the server and 1 rate limiter. So as promised, the attacker corrupts the server and 1 rate limiter 0. Then he instructs the server to send the first message of the decryption protocol to rate limiter 0. Since decryption is only 2-round, then by this point the rate limiter should already learn whether the password is correct, just from the first message. With these challenges in mind, let us quickly go through the high-level ideas of our scheme. The basic idea is that instead of using a general-purpose MPC, we use a special-purpose one, so as to emulate the rate limiter by the so-called secret sharing in the exponent technique. We require 3 main ingredients, namely a secret key encryption (SKE), a decisional Diffie-Hellman hard group written additively, and 2 hash functions h0 and h1 hashing bit strings to the group. Encryption works as follows. A ciphertext consists of a single symmetric key encryption ciphertext of 2 group elements C0 and C1, which consists of the message padded with the usual sorted hash of the password, together with some pseudo-random value computed on the sort and with the key RK. And the key RK is secret shared into RK1 to RKM and distributed to the M rate limiters. To decrypt, the server inputs Y0 and Y1, which can be computed by taking C0 and C1 and removing the sorted hash values. And if the password is correct, it should be equal to this sum right here. The rate limiters input the secret shares of the rate limiter key RK, and these parties jointly compute this function here, which should be equal to the message if the password is correct. In the paper, we present 2 variants of the decryption protocol. The first variant is with 7 rounds, and it achieves fine-grained rate limiting, which means that it rate limits only failed decryption attempts. There is another variant with 6 rounds, which achieves coarse-grained rate limiting, namely that it rate limits both successes and failures. We think that the 6-round variant is more practical because it offers sufficient security and is more efficient. We have evaluated the efficiency of our scheme and compared it to that of PHE. Note that a slowdown is expected, but we want to know by how much to see if it is worth it for the increased security. It turns out that in terms of latency, TPHE is around 2 times lower in encryption and around 4 times lower in decryption. Fortunately, the latencies are still well within the realm of milliseconds. In terms of throughput, we can see that the amortized time per request for both encryption and decryption, for both the server and the rate limiters, scale linearly with the corruption threshold T. To conclude, if you own a system which uses password authentication, you should upgrade your system to use TPHE now. To help you do that, our startup company, Umbra Security, is there for you. Currently, we are looking for investors, customers, and also collaboration partners. If you have any questions, feel free to contact me by email. This has been Russell Lai, and thank you for your attention.